Okay, so we are starting exercise 1.1 now. So the question number 1 says use Euclid's division algorithm to find the HCF of these numbers. First of all, what is HCF? If we talk about the full form of HCF, it is the highest common factor. Highest common factor, right? Also we call it as GCD, greatest common divisor. So what does it mean? A number, the greatest number or highest number which can divide these two numbers will be called as HCF. Okay, so by Euclid's method we'll try to find out HCF of these two numbers, right? So what is the procedure? First of all, out of the two numbers, the larger number is termed as A. So if we talk about 135 and 225, the larger number is 225. So we'll say this is A. And the smaller number will be termed as B. Okay, so A is 225 and B is 135. Right? Now, we'll apply the division lemma or division algorithm. What does it say? It says A is equal to BQ plus R. A is always equal to BQ plus R. Right. So what does it mean? I'll explain you. Let us say we are taking some A equal to 10. Okay. So I've taken A equal to 10. Let us say. Now choose a B which is smaller than 10. Any number. Choose any number which is smaller than 10. Let us say 4. Right. 4. So we can write 10 as 4 into 2 plus 2, right or wrong, check it. 4 2s are 8, 8 plus 2, 10 is equal to 10. Understood? So for a which is larger than B, it is always true that A is equal to B into Q plus R, where Q is the quotient and R is the remainder. I can explain this whole thing like this also, that if we divide A, that is 10 in this case, by B, which is 4 in this case, what I'll get? 4 2s are 8, isn't it? 4 2s are 8 and 10 minus 8 is 2. So this 10 is A, 4 is B, this quotient is Q, and plus this remainder is R. And this whole procedure is called A is equal to B cube plus R is called Euclid division lemma. Right. So when we write this division process like this is called Euclid division lemma. Understood? So any larger number can be represented as in the form of BQ plus R, where B is a smaller number. Right. So A is actually, what do we call A? Dividend, B divisor, this Q quotient, and this R remainder. So dividend can be written as divisor into quotient plus remainder. Okay, so here some conditions are also given, that dividend should be greater than divisor always, and remainder can be 0 or any number less than B. Okay, so in this case remainder can be 0 or any number less than 4. Understood? This is Euclid division lemma. Now we'll apply this lemma in this question. So A is 225, B is 135. What I've written is 135 ones are 135 plus 90 would be 225. Okay, so in this case this is A, this is B, this is Q, and this is R. Understood? Simply divide 225 by 135, you will get quotient as 1 and remainder as 90. Now after doing this, you look at this term. Now we'll take this term as A, which was in the previous step it was B. Now we'll take it as A, right? And this remainder as B, and repeat the lemma. So see again, A, that is 135, is equal to B, 90, into 1 plus 45. How we get it? We just simply want to divide 135 by 90. So if you divide 135 by 90, what you'll get? 135 by 90. So 90 ones are 90, isn't it? Simple division. Minus करेंगे तो we'll get 45. Okay, so A, that is 135, is equal to B, that is 90, into Q, Q is 1, plus remainder 45. I hope you got this point. Now after this step, again we'll do the same process. This time we'll take A 90 and B 45. We are repeating the previous step. You see, this we took as A and this we took as B. Now this we are taking as A and this we are taking as B. Okay, so again we'll divide 90 by 45. This time very simple. 45 to the 90 and therefore the remainder will be 0. So as soon as you get the remainder 0, right, whatever was the divisor in this step, that will be the HCF. I'll repeat myself. As soon as get remainder 0, whatever the divisor is there, it will be your HCF. So now HCF is 45. So this remainder is 0. You may get it in first step, second step, third step, or fourth, fifth step. Whenever you get remainder as 0, you will stop there, right? And the divisor will be your HCF. Okay, now we'll do second part. See carefully. So two numbers are here. One is 38220. Of course, it is a larger number compared to 196. So this number 38220 will be A and 196 will be B. Okay, and again we'll apply the division lemma. What we'll do, we'll divide 38220 by 196. So after dividing, you will see that your quotient will be 195. That is 196 into 195. Straight away you will get 38220 and your remainder will be 0. So what I said in the previous question, as soon as you get remainder 0, it may be in first step, second step, third step, or in any step, you will not proceed, like you will not do the question further. You will stop there only, right? And the divisor, what was the divisor in this question? 196. This divisor will be your HCF. So your HCF is 196. So you see, even in the first step, you may get the answer. Okay, we'll move towards the third part. 867 need to be divided by 255. Again, because 867 is larger compared to 255. So what has been done? 867 is equal to 255 into 3 plus 102. Simply, I'm not showing division here, but if I show simply this 867 divided by 255, excuse me for the writing, you can understand it, I guess. 255, right? 3s are 255, 3s are how much it is? 5 3s are 15. Then 3 5s are 15 plus 1 16, 6, 1, 3 2s are 6 and 7. And on subtracting, you'll get 7 minus 5, that is 2. And 86 minus 76, that is 10. So what you got? Quotient as 3, see, here we write quotient, plus remainder as 102. Understood? So after doing this step, now we'll take this as A, 255 as A, and 102 as B, and repeat the step. So A is equal to B into Q plus R. Again, this time we have to divide 255 by 102. Simply 102 2's is 204, and remainder will be automatically 51. Isn't it? 204 plus 51 will be 255. So simply you can divide 255 by 102. And 102 2's will be 204. And on subtracting, you will get 51 as remainder. Now we'll repeat the step. Now we'll divide 102 by 51. And this time simply 51 2's is 102 and you'll get remainder 0. So I hope you know the division, how to divide. And then the question is very easy. We will stop here after getting 0. Okay. And the divisor in this step will be RHCF, that is 51. Okay, we'll proceed to the next question. Now what is given in this question? Show that any positive odd integer is of the form 6q plus 1, 6q plus 3, 6q plus 5, odd integer. Positive odd integer is of form this. So what to do? We know according to the Euclid division lemma, A is equal to BQ plus R, isn't it? Where B is always less than A and R is any number from 0 up to B, less than B, right? So now we need to prove that any odd integer, positive integer, should be of this type. What we'll do? Simply in place of B, we'll put 6. In place of B, we'll put 6. So A will be equal to 6q plus R. So if somebody asks why we have put 6 here, simply because in the question we require 6, that's why. And what are the constraints on R? What should be the value of R? Simply R should be less than 6 and it may be equal to 0 also. So from 0 up to 5, 0, 1, 2, 3, 4, 5, the values of R may be. This is the constraint on R. Constraint means बंधन. ये बंधा हुआ है, ये 6 से बड़ा नहीं हो सकता, ये 6 से छोटा ही रहेगा. Whatever the value of B is here, R will be less than that only, and the smallest value of R is 0 always. Okay, so from 0 up to that value you can write. Okay, now so if I put R is equal to 0 here, we'll get A is equal to 6q. See, if you put R is equal to 1, we'll get A is equal to 6q plus 1. If you put R is equal to 2, we'll get 6q plus 2. R is equal to 3, we'll get 6q plus 3. R is equal to 4, we'll get 6q plus 4. R is equal to 5 means we'll get 6q plus 5. Isn't it easy? Just put the values of R. Now, if we talk about 6q plus 1, we can write 6 as 2 into 3. Okay, 2 into 3. So 6q can be written as 2 into 3q and just plus 1 as it is. Now this 3q, I am naming it as k1. K1 means some constant. So this is 2 into k1 plus 1. I am repeating myself. This 3q, I am saying, let us say this 3q is equal to some number k1. Right. So in place of 3q, I am writing k1. So I am writing 2k1 plus 1. Similarly, if we go to 6q plus 3, right? So first of all, this 3 I can write as 2 plus 1. This 3 I can write as 2 plus 1. Out of this 6q plus 2, I can take 2 common. And now this time, this 3q plus 1, I can name it as k2. Previously, 3q I named as k1. This time 3q plus 1 I am naming it as k2. So I can write it as 2k2 plus 1. Okay. Now let us further proceed to 6q plus 5. And 5 I am writing as 4 plus 1. Now see this pattern carefully. Here 3 I wrote as 2 plus 1 and 5 I am writing as 4 plus 1. Now this 6q plus 4, out of this 6q plus 4, because 4 plus 1 is 5. So out of this 6q plus 4, I am taking 2 common. And now inside the bracket, I have 3q plus 2. This 3q plus 2, I can name as k3. Now see the pattern. 3q I named as k1, 3q plus 1 I named as k2, 3q plus 2 I named as k3. Now this can be written as 2k3 plus 1. Okay. Now after this, you can see easily that 6q plus 1 is of type 2k1 plus 1. That is 6q plus 1 is equal to 2k1 plus 1. 6q plus 3 is of type 2k2 plus 1. And 6q plus 5 is of type 2k3 plus 1. Now I'll make it very clear to you what we have done, why we have done. Okay, see how we have done, we have already seen. So if something is of type 2 into k, k may be any positive integer. So if anything is of type 2 into k, it will be an even number. For example, If we take k is equal to 0, 2 into 0 will be 0. If we take k is equal to 1, 2 1s are 2, k is equal to 2, 2 2s are 4, k is equal to 3, 2 3s are 6, k is equal to 4, 2 4s are 8, and so on and so forth. We can take any value of k and get all the positive even integers, right? So it is clear that 2k will be a positive even integer. And if we add 1 to this positive even integer, what we'll get? We'll get an odd number, odd positive integer. For an example, 4 is a positive even integer. If we add 1 to it, what we'll get? We'll get 5, which is a positive odd integer. So it proves itself that 2k plus 1 type of terms are positive odd integers, right? So it is hence proved 6q plus 1, 6q plus 3, 6q plus 5 will be a positive odd integer. I hope it is clear. Now we'll proceed to question number 3. So the question says, an army contingent of 616 members is to march behind an army band of 32 members in a parade. They always walk in front of the whole contingent, right? And we want to arrange these contingent members and band members in such a way that they make maximum number of columns. Okay, so you must have seen in the parade that these contingent people or band people always walk in straight lines. We call them as columns, right? So simple, I'll not stretch the question too much. Simply, you just need to take the HCF of 616 and 32. So using the Euclid division algorithm, what we'll do? 616 is the larger number amongst the two. So A is 616, B is 32. If we divide 616 by 32, you'll get quotient as 19. I'm not doing the division here. You can do it by yourself, and remainder will be 8. After doing this, you'll see this term will be A now, and this term will be B. And we'll repeat the process. A, that is 32, is equal to B into Q plus R. So this time 8 for the 32 plus 0. Straightforward, it will be divided without leaving any remainder behind, or we can say remainder is 0. So as soon as you get the remainder 0, the divisor is your HCF. So what is the divisor? Divisor is 8. 4 is quotient, 0 is remainder. So HCF will be 8. It means there will be 8 columns in which all contingent members and the band members can be accommodated, right? So simple, I guess it is. Next we'll do question number 4. Use Euclid's division lemma to show that square of any positive integer is either of form 3m or 3m plus 1 for some integer m. So we need to show that square of any positive integer is of the type 3m or 3m plus 1. So what we'll do, first of all, we'll apply the Euclid division lemma, that is A is equal to BQ plus R, and in this question, in place of B, we require 3. So we'll just put B is equal to 3. So now the lemma is A is equal to 3Q plus R. And what values will R have? 0, 1, 2, simply less than 3. Okay, already it has been explained. The value of R is less than this B. So 0, 1, 2. So the value of A will be 3Q plus 0, that is 3Q, 3Q plus 1 and 3Q plus 2. Right? Got it? Then on squaring, because in the question it is given that we need to square the positive integers, and after squaring the answer should be of this type. So what I'm doing, I'm squaring these terms. Okay, so individually also you can solve, and like this also you can solve. So on squaring 3Q, right, see only this term. On squaring 3Q, you will get 9Q square, right? 9 can be written as 3 into 3. And then this whole 3Q square will be named as K1. This term I'll name it as K1. Okay, so now this whole thing will be 3 into K1. That is, it is of the form 3 into something, right? In place of K1, you can simply name it as m also. So it will be like, after that you can say it is 3m, which is written here, right? So what I have done, I have just named it as k1, and 3 into k1 will be your answer. If we square this term, we have to follow the identity a plus b square is a square plus 2ab plus b square. So a square is 9q square, and the square of 3q is 9q square, plus 2 into a into b. So 2 into 3q, that is 6q, into 1 will be 6q. Understood? This is a, this is b. So 2 into a into b, that is 2 into 3q is 6q, 6q into 1 is 6q, plus b square. B square means 1 square, that is 1 only. Understood? Now out of these two terms, 3 can be taken common, so I have taken 3 common. So here it is 3q square, and here since 3 is taken outside, only 2 will be there. This whole term we can name as k2, and now it would be 3k2 plus 1. In the previous solution, I have taken this as k1, so it was 3k1. In this one, I am naming it as k2, so it will be 3k2 plus 1. Now we'll go to the next term, that is 3q plus 2. After squaring, we'll get a square, that is the square of 3q, which is 9q square, right? Then plus 2ab, plus 2ab means 2 into 3q into 2. 2 into 3 is 6, 6 2 is 12, 12q. Okay? And plus b square means square of 2, that is 4. Understood? Okay, now this 4, I'm writing it as 3 plus 1. 4 I'm writing as 3 plus 1. And out of these 3 terms, I am taking 3 common. So after taking 3 common, here there will be 3q square, here there will be 4q, and after taking 3 common from this 3, only 1 will be remaining. Plus, now 1 is there. Okay. Now I'll name this term as k3. So it will be 3k3 plus 1. So you are seeing what answer you may achieve, you may get 3k1, 3k2 plus 1, 3k3 plus 1. What was the question? Question was that on squaring an integer, you will get something of type 3m or 3m plus 1. So m is nothing but a integer. Okay. Here also k1, k2, k3 are nothing but integers only, right? So we have proved what was required. We have achieved this 3m, 3m plus 1, 3m plus 3. Instead of m, we have k1, k2, k3. That is all right, because m is also an integer and k1, k2, k3 are also integers. So arbitraries can be used. There is no such issue that only m should be there, right? So where k1, k2, k3 are some positive integers, hence it can be said that the square of any positive integer is either of the form 3m like this, or it may be of the form 3m plus 1 where m is some integer. Understood? Okay. Question number 5. So the question says, use Euclid division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. So how to do this? Again, we'll apply the Euclid division lemma, a is equal to bq plus r. Now, in the previous question, I told you that since the question is asking us to prove 3m type, so we have taken b is equal to 3. But in this question, they are asking us to take to prove 9m. So some students think that the value of b should be 9 only. But no, we'll just take the value to be 3 only. Why so? Because if we take b 9, r will be having 9 different values, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, isn't it? So if we have 9 different values of r, there will be 9 different values of a also. What they would be? A is equal to 3q, 9q, a is equal to 9q plus 1, 9q plus 2, 9q plus 3, 9q plus 4, 9q plus 5, 9q plus 6, 9q plus 7, 9q plus 8. And then we have to cube all those 9 terms. It would be a tedious job, right? So instead of 9, we are taking 3, and don't worry, we'll reach our solution easily. Okay, so I've taken b equal to 3 and r, the value of r will be 0, 1, 2, that is natural numbers less than 3, whole numbers less than 3. Okay. So the first term we will get is 3q plus 0, that is 3q. The next term will be 3q plus 1 and the next term will be 3q plus 2 after putting the value of r. Okay, now I'm cubing them. First one, cubing 3q. Cube of 3 is 27 and q cube. Now what do we need to prove? We need to prove that it is of the type 9m. 9m, isn't it? So what I'll do, I'll write 27 as 9 into 3 and q cube is already there. Okay, 27 I've written as 9 into 3. Now this whole term I can name as k1 or m, whatever you want to put it as. Put it equal to, right? So this whole term we can put it equal to m or k1, whatever you want to do, you may do. So 9m will be your answer. So we are reaching our answer easily. Once again, you see, we either need to prove it equal to 9m, 9m plus 1 or 9m plus 8. So 9m we have already proved. Case 2, now we'll cube the second term, and before cubing it, we need to know the formula of cubing. A cube plus 3a square b plus 3ab square plus b cube. I repeat, a cube plus 3a square b plus 3ab square plus b cube. Okay, so while cubing, take it as a and this term as b. So a cube, see, right? Then 3 into a square. A square means 3q square. That is 9q square. 3 into a square. That is 9q square. Into b. And what is b? B is 1. So no need to write into 1. And if you multiply it, what we'll get? We'll get 27q square. Okay. Similarly, then we'll do 3 into a into b square. So 3 into a, what is a? A is 3q. 3 into a into b square. And what is b square? That is 1 square. Okay. No need to write, but still for explaining I am writing. 3 3s are 9q you will get. And plus b cube, that is 1 cube, that will be 1 only. Okay. So out of these first 3 terms, you can take 9 common easily. So here you will get 3, 3, 9 ones are 9. And now putting this whole thing equal to m or k2, you may put it equal to k2 as I have done in previous question. So this will be 9m plus 1. This we need to prove. Okay. So further, if we go now, this third term, I'll explain you. This 3q we have done, this 3q plus 1 we have done. Now 3q plus 2 we are going to cube. So cubing both sides, a cube plus 3a square b, same formula, 3a square b, right? Plus 3ab square plus b cube. Okay, same formula we have applied. You may calculate it by yourself, you will get the same answer. Okay, so out of these first 3 terms, 9 can be taken outside common. So 3 will be there. 9 6 are 54, 9 4 are 36. Okay. This whole term you can put it equal to k3. In some books they have put it equal to k3. Some places they have put it equal to m. You can do it, no problem. So it will be 9m plus 8. And now you have proved that the cube of any positive integer is of type 9m, 9m plus 1, 9m plus 8. And this is the end of the exercise. I hope you understood it. Even if there is any doubt, you may ask me, right? So do this work in your notebooks. If any doubt, ask me. Okay. Bye.